All right, welcome back, guys. We're going to be starting chapter 5 and we're going to do section 5.1. So, chapter 4 was about discrete random variables and discrete probability distributions. So, like, for example, the binomial probability distribution. Now we're going to be looking at continuous random variables. So, a random variable that can assume a value that's within some interval, okay? And we're going to be studying in further detail something called the normal distribution, and then something that's related called the standard normal distribution, okay? All right, so let's look at the learning objective. So we're going to interpret graphs of normal probability distributions, and then we're going to look at finding areas under the curve. Okay, this will make more sense later on, but first thing we're going to do is we're going to start talking about the normal distribution. So we've talked about this some when we talked about the empirical rule and how much of the distribution would be within one standard deviation or two standard deviations of the mean, etc. We're referring to this this normal distribution, or that symmetric bell-shaped curve. Okay, when a random variable is continuous, guys, and it's normal, then it'll have this shape of distribution. Okay, and I've got a picture right down here. Okay, so this bell shape, and it would be symmetric. All right, so let's talk about some properties of this. Well, one of the big properties is that the mean, the median, and the mode are all going to be equal. In other words, they're all going to be right here in the center of the distribution. The mean and the median are the center of the distribution, okay? And then we start measuring how far away a value of x is from the mean in terms of standard deviations. So we see this sigma again, okay? So this point right here would represent a value that's one standard deviation above the mean. This would represent a value that's two standard deviations above the mean, etc. And then on the other side, these would be values 1, 2, and 3 standard deviations below the mean, respectively. It is bell-shaped and it's symmetric. The total area under this curve is 1, okay? 1 or 100%. And the reason for that is because, as you know, the sum of all the probabilities in a distribution have to be 1. Think about those discrete probability distributions that we talked about in chapter 4, okay? So therefore, the area under this normal distribution must be equal to 1. And then some other properties. The normal curve approaches but never touches the x-axis as it extends farther and farther away from the mean. And what this shows is that as values get farther and farther from the mean, their respective probabilities get smaller and smaller. In other words, closer and closer to 0, okay? So theoretically, there's still probability out there, but practically, there's really not. And then I guess I will go ahead and mention this, although we're not going to talk about it much. A standard or a normal curve like this has what are called inflection points, and it's these points right here. And they occur at values of x that'll be 1 standard deviation below the mean and then 1 standard deviation above the mean. And what's significant about these values is that if you look at this like it's a function, it's at this point right here where the steepness of this function stops increasing and actually starts decreasing. Okay, so if you're riding along this, it just keeps getting steeper and steeper and steeper and steeper, and then once it hits this point, it's still steep, but the steepness starts to decrease. Okay, and it just keeps starting to decrease, and then it hits this point again, and then the steepness starts to decrease. Well, yeah, the steepness starts to become less steep. This would be like the steepest point right here, and then this is the steepness starts to level off after this point. And you can see as it comes out here, it really starts to level off. So anyway, this really has more to do with calculus, and we're not going to be concerned much with locating the inflection points for a normal distribution, for a normal curve in this class. All right, well, those are some properties. Like I said, some of these we've talked about before. That 68% of the area is going to lie between one standard deviation below and one standard deviation above the mean, and that's what this means. This is the mean minus sigma, and this is the mean plus sigma. Okay, so graphically that means from this point to this point, you'd have 68% of the area under this curve right here. And then 95% of the area is going to lie within 2 standard deviations of the mean. So in other words, from here to over here, you're going to, whatever those values of x are, within those 2 values of x, you're going to encapsulate 95% of the distribution, 95% of the values of that continuous random variable. And then guys, 99.7, or in other words, almost the entire distribution, will be between 3 standard deviations away from the mean. Okay, so from here to here, and you can see that's practically that entire distribution. There's very little probability left out here beyond 3 standard deviations. All right, and then a few other things we'll say. So if you remember, we use histograms to graph those discrete probability distributions. And it's because they were discrete. There weren't infinitely many values of x, right? We saw some that had like 5 or 6 values of x. So to show the associated probabilities with those values of x, we use bars. But when x can be infinitely many values between a starting 2 endpoints or an interval, then we don't get bars. Those bars become infinitely small, and we actually get a smooth curve like this. Okay, this curve is not made up of bars. Well, it sort of is made up of bars, but they're infinitely narrow. And then we use what are called probability density functions to graph these continuous probability distributions. Okay, and then let's see. Oh, the function, it can never be negative, so you're never going to see it dip below the x-axis, because for every value of x, that represents an event, and every single event has to have a probability greater than 0, or greater than 0. All right. Furthermore, guys, every graph or every bell curve, and these will differ depending on distribution. Each graph is going to be completely dependent upon the mean and the standard deviation. Okay, so the mean will tell us where the distribution is centered along that horizontal axis, and then the standard deviation is going to tell us how spread out is that distribution. Okay, is it going to be a very narrow bell curve, or is it going to be a wider bell curve? And down here we've got some examples. I'm going to zoom in just a little bit here. All right, so let's look at these 3. You'll notice these first 2 guys, the mean is the same. It's 3.5, and we don't know what this is measuring, nor does it really matter. So you can see the center of the distribution is right here above 3.5 on the horizontal or x-axis. But notice how distribution A is much more spread out. And the reason is because the standard deviation is 1.5 as opposed to the standard deviation for distribution B is 0.7. Okay? So if you remember us talking about that coefficient of variation, the coefficient of variation for distribution B is much smaller. So that's why this is a much narrower distribution as opposed to that of distribution A. Okay, you guys remember the coefficient of variation was the standard deviation over the mean. Now let's look at this other one here. This other one's centered at 1.5 because that's where the mean is, and then its standard deviation is 0.7. So you cannot say how spread out the distribution is, just the raw distribution, unless you know both the standard deviation and the mean. Okay, because the mean puts into reference how spread out it is, because you compare the standard deviation to the mean, and that's called the coefficient of variation. So that really tells us how spread out the distribution is. And here's a real life distribution here. Lots of things, guys, are normally distributed. Okay, that just means that if you were to go out and start taking samples, and if you were going to make a frequency distribution or a frequency histogram by sampling lots of things, these could be like the heights of trees in a forest, or the heights of a specific species of a tree in a forest, or the circumference of the trunk of a specific species in a forest, or the lengths of a specific species of fish in a lake. And you were to make a histogram out of all those values, and then it would have a shape like this, a bell shape. Okay. Heights are normally distributed. People's IQs, those are normally distributed. The weights of newborns, like we see here, these are normally distributed. So you can see the center of the distribution is about 3,300 grams. Okay, and this would be about 7 pounds. Okay, so that would be about average, and then you can see it kind of falls off after that. And we don't know actually what the standard deviation here is, but you can see. So, that's why, let's see, 4,500 grams, what would that be? That would be over a 9-pound baby. Maybe like 9.5 to 10-pound baby. So that's why you see the height of this distribution not very high, because babies of that size are rare. And similarly, on the other side, babies that are significant, 4 or 5 pounds, those are also relatively rare as well. Okay, but anyway, this is just a real-life example of data, weights of newborns in particular, that is normally distributed. Okay? All right. So now let's start talking about this thing called the standard normal distribution. So what's the difference in this and just a normal distribution? Well, lots of things are normally distributed. Okay? They're bell-shaped, and they have their own specific mean. Okay? But what we can do is we can standardize those distributions by finding their z-scores. If you remember from Chapter 2, I believe it was, Chapter 2, Section 2.5, the z-score is basically the number of standard deviations away from the mean that a value is. So if the z-score is positive, it's going to be to the right of the mean, and if the z-score is negative, it's going to be to the left. So a z-score of 1 means that that particular value in that distribution is 1 standard deviation above the mean. Okay? And if you remember, this is the formula that we use to find it. Whatever the particular data value is, minus the mean of the distribution divided by standard deviation. Okay? So, what is the standard normal distribution? Well, it's a distribution in which the mean is 0 and the standard deviation is 1. And that very first one that we saw, this is a standard normal distribution. If we let the mean be 0, and if we let sigma here be 1, okay? So, the actual raw data itself is probably not going to have a mean of 0 and a standard deviation of 1. But when we convert everything into a z-score, then the distribution of these z-scores we say is normal, and we call it a standard normal distribution. Okay, so a z-score of 0 means that that particular value is not above or below the mean. It is the mean. And then any z-score that's positive would be to the right of the mean, and any z-score that's negative is to the left. So the standard normal distribution itself is actually the distribution of z-scores, okay, from any other normal distribution. So we say that anything that's normally distributed can be standardized. Okay, or in other words, all those actual data values in that distribution, they can all be turned into z-scores. And from all those z-scores, we get the standard normal distribution. Let me see if I... yeah, here would be an example. See, the mean here is 0, and then wherever z, this is a distribution of z-scores. We're going to talk more about this table here in a minute, but, a z of -1, that just represents a value that's 1 standard deviation below the mean, okay? All right, so it says when each data value of a normally distributed random variable x is transformed into a z-score, the result's going to be the standard normal distribution. Let's see. And then in the following sections, we're going to see how we can use the standard normal distribution to calculate probabilities for a wide range of different distributions. So a wide range of other normal distributions, they can all be standardized. And because of that, we can find probabilities, okay, that x lies within a certain range of values, or that z lies within a certain range of values. All right, so the first thing we're going to do is we're going to look and see how could we calculate the amount of area under the curve corresponding to different values of z. Okay. Let's see here. Let's look at these additional properties first. So the cumulative area is going to be close to 0 for z-scores close to -3.49. So what this means, I'm going to draw you a graphic here. So remember, with the standard normal distribution, the mean is 0. And a z-score of -3.49, that means it's a value that's 3.49 standard deviations to the left of whatever the mean is. So that's actually a long way away. Because remember, most of the distribution lies within 3 standard deviations, so this is beyond 3. Okay? So when it says right here the cumulative area just means the area to the left of this z-score. In other words, the area that's in this part of the tail right here. And it says that it's almost 0. There's hardly any probability out here beyond that tail. Okay? And then the cumulative area will increase as the z-scores increase, because the cumulative area, guys, is the area to the left of the z-score. So as my z-scores increase, the area that's opened up under this curve is increasing as well. And if we were to keep doing this all the way to z equals 0, well, z equals 0 corresponds to the mean of the distribution. That means I would have half of the distribution. Okay? Exactly half, because this is a perfectly symmetrical distribution. And this also means that there's another half, or 0.5 of the distribution, to the right of the mean. Okay? And then furthermore, if we just kept going to the right, then almost the entire distribution, or close to 1, would be to the left of positive 3.49. Okay? Okay, everything to the left of 3.49 would almost be the entire distribution. Because anything beyond 3.49 standard deviations from the mean is extraordinarily rare. Okay. But anyway, these are some properties, and we're going to talk. We'll be alluding to some of these more as we progress through this section. Okay, so we want to get some practice trying to figure out how much area is to the left of a specific z-score. Okay. And fortunately for us, we can use technology to do this. Okay. So let's say we wanted to find the cumulative area for the area to the left of a z-score of negative 0.99. So negative 0.99 is about negative 1. So in other words, how much area is to the left of z equals negative 1? Okay. Or in other words, what's the probability that z would have a value that's less than negative 0.11? Okay. All right, so I think, though, I'm going to draw you another graphic right here. You'll learn that sketching out these standard normal curves is really going to help you kind of visualize what you're trying to find. So the mean is right here. It's 0. Negative 0.99, that's about negative 1. That's about 1 standard deviation to the left of the mean. So what we're trying to do, the cumulative area would be how much area is under the curve to the left of that value of z. Okay. In other words, how much area is in this portion of the tail that I'm shading right here. Well, the calculator will help us do this, but you've got to tell the calculator, you've got to give it a starting value and a stopping value. Okay. So because this distribution technically goes on forever, here we go. Because it goes on forever to the left, we can sort of say that we're trying to find the area under this curve from negative infinity all the way up to negative 0.99. Okay. And we could tell the calculator that. There's a function in the calculator called the normal CDF, and I'm going to pull it up here for you. If you come over here to distribution, so you hit second and then the variable key, normal CDF. So this means the normal continuous density function, or not continuous, I'm sorry, cumulative. Not sure what I was thinking there. So you hit enter, and if you've got one of the newer calculators, it'll look like this. If you've got one of the older calculators, you have to type these in parentheses. So you have to tell the calculator a lower bound, you have to give it an upper bound, you have to tell it what the mean and the standard deviation are, and then you just paste it into your calculator. Well, anytime we're working with the standard normal table, the mean and the standard deviation will always be 0 and 1. Now, if we're working with a raw distribution itself, then the mean and the standard deviation will just depend on that distribution, okay, unless we've standardized it. All right, so the question then here is, if my lower bound is negative infinity, how do I write that? Well, guys, there's hardly any area out past, say, even negative 10, okay? So typically what most people will do is they'll put in here a negative 1, and then they'll hit this, let me find it. Oh, this key right here, right above the comma. Let me just clear this so I can show you. They'll put negative 1, they'll hit the second key, and then they'll hit the comma key. And this E is for scientific notation. I've mentioned this before. And when I give it an exponent of 99, really what this is, it's like negative 10 to the 99th power. Well, that is a tremendously huge negative number. So we can say, well, this number is close enough to negative infinity. We're just going to let this be the left hand, the lower bound. Okay. And then the upper bound is whatever z-value you're working with. So in this case, it's negative 0.99, okay? And because this is a standard normal curve, I'm going to leave these values the same. I'm going to paste this into my calculator. See that? I'm going to hit enter, and it'll tell me. And it's always going to be as a decimal, right? So this agrees with what we have here in the notes. So the area from basically negative infinity all the way up to z equals negative 0.99 is about 16.1%. Okay, so that means the rest of the 100% is on the right side, to the right. Okay, it'd be about 84% to the right. But anyway, that's how you do it using the calculator. Let's see here. And this just kind of goes over what I just told you. Now, if you were trying to find the area between two specific z-scores, then the lower z-score would be your lower bound, and the upper z-score would be your upper bound. Okay. Now, we also could have found the area to the left of negative 0.99 using a z-table, or a standard normal table, and that's what I want to show you now. Okay. Okay, so this is a picture of one, guys. So the z-values are listed over here to the nearest tenths place, and then to get the hundredths place, you look in this row. Okay. So our z-value was negative 0.99. So here's negative 0.9, and then to get that other 9, I look right here. And so it's in this column. So here's negative 0.9, and this is the column that has the 9 and the hundredths. So it would be 0.1611, which as a percentage is about 16.1%. Okay, and notice here, look, it's showing you, it's got shaded what you're trying to find. You're trying to find the area, the cumulative area, to the left of z. So in other words, all the area that's under this curve from negative infinity all the way up to a specific value of z. Now let's scroll down here. Let's look and see whenever, here's negative 0.0, and up here is 0.00, so this is the same as 0. So when z is 0, there is 50% of the area to the left, which means the other 50% of the area is to the right, which we know, because with these symmetric normal distributions, we have half to the left of the mean and the other half to the right of the mean. Here would be an instance in which you were trying to find the area between a lower z-score and a higher z-score. And here's an example. See, now we get into the positive values of z. So here we're to the right of the mean. So how much area is going to be under the curve? Well, it's going to be more than 50%, and all these values are more than 50%, all the way up to look, as far as it'll go is 3.49. And look how much area we've got. That's almost 1. Okay? So that's why the notes were saying before that there's hardly any area beyond that under the tail. There's a little bit, but not really enough to worry about. But anyway, that's how you would use the table if you wanted to find any of these cumulative areas under the curve. Okay? All right, let's continue. Okay, so we're going to look at a couple examples. We want to find the cumulative area that corresponds to a z-score of 1.15, and then again for a z-score of negative 0.24. And we're going to use 3 different methods to do this. These are actually already done for us. Okay, these are the 2 graphical representations. Let's try to find the cumulative area that corresponds to a z-score of 1.5. So in other words, 1.5 would be about right here. It's 1.5 standard deviations above the mean. So how much area is to the left? Well, it tells us, but if we had to find it ourselves, we could use the table. So I'll show you that again. So a z-score of 1.15. So let's go to the table. You want to come down here to the positive values of z. Okay, so here's 1. We need 1.1, and then 5 is in this column here. So 1.15, you just match these up, so it looks like it's in this column and in this row. So it's this value right here, 0.8749. And that's what we've got. That's the area to the left, or in other words, 87.9% of the distribution is to the left of this z-score. Okay. Now, using the calculator, this is the way you would do it. You would go to distributions again, or you could just reuse that same one. You want your normal CDF. You're going to let this lower bound be negative infinity, but you're going to change this upper bound. Now we want a z-score of 1.15. Okay, and you're going to keep these the same because we're still working with the standard normal distribution. And you enter again, and we get the same thing, 87.49%. Okay, and then if you want to use Excel, you can, and I'll show you how to do that. So what you have to do is hit equals. You have to come over here. You can see I already pulled it up, but you would go to More Functions under your statistical package, and it's going to be under Normal. And it's this one right here, normal.distribution. Okay, so if I click on that and click OK, it asks me for X. X here means Z. So what is the Z value that we're going to? Well, we're going up to 1.15. And the mean is 0, because this is a standard normal distribution. The standard deviation is 1. And then down here where it says cumulative, you're going to type in there true, because you want the cumulative area. Okay. You can see it's already calculating it right here for you, but if I hit enter, it'll give it to me in this cell, 0.8749. Okay, so again, 87.49%. All right, and then for the other one, a z-score of negative 0.24. We've got it graphed for us right here, negative 0.24. That's a little bit to the left of the mean. Okay, so how much area is to the left of that z-score? Well, using my table, my negatives are down here. It was negative 0.24. So here's negative 0.2, and then it would be this would be negative 0.20, 0.21, 0.22, 0.23, 0.24. So it's about 40.13% according to the table. And that's what we see here, 40 point. Well, there might have been some rounding involved there. Let me look back over here. Oh, here it is, yeah, 40.52, okay. If we want to use our calculator, you use that same normal CDF. In fact, I'm just going to hit second and then enter for entry. And I'm just going to change that value of z. I want it to be a negative 0.2. Is it 24, I believe? Yeah. 24. Now, I wrote over some of my other stuff here, so I'm just going to have to replace it. We'll put a comma, 0, a comma, and a 1. I'm just inputting the mean and the standard deviation for the standard normal distribution. I'll hit enter, and we get the same thing, okay? This one would round to a 2, so 40.52%. And I'll show you one last time how to use Excel. And we're going to look at some examples. I'll just select another cell. So click another cell. We can say equals. Select this norm.distribution. Our new z-score is negative 0.24. The mean, of course, is 0. And the standard deviation is 1. And we want the cumulative area, so I'm going to type in here true. Okay. I'm going to hit enter. And it gives it to us. Okay. So that's how much area is under that curve. From the left side, from negative infinity, all the way up to that specific value of z. All right. Well, I think from here on out, guys, I'm just going to be using my calculator. But if I had to do this a lot, I would probably set me up a little Excel file in which I could enter a specific value of z, and it would go ahead and spit out my cumulative area. Or I could set it up to where I could enter my lower bound, my upper bound, my mean, and my standard deviation. And I could set it to where it would reference those 4 cells, depending on what I put in there, and then it would spit out the area, okay? The corresponding area, but I'm not going to fool with that at the moment. Okay, so let's look at some other examples here. So it says, find the probability of z occurring in the indicated region of the standard normal distribution, okay? So you can see here, we've got everything shaded to the left of z equals 0.69. So I'm going to use my old trusty calculator again. I'll go get the normal CDF. I'm keeping this the same because I'm still going to be going from negative infinity all the way up to this value of z. So I'm going to change my upper bound. Change it to 0.69. Paste this in here, and we're going to get 0.7549. So I said P because the area under the curve actually represents the probability. Okay, we'll tie this to that later on. All we're doing now is just getting some practice trying to figure out the area under the curve. Okay. Now this as a percentage would be 75.49%. Okay, so you've got about 75% of this distribution to the left of z equals about 0.7 right there. Okay. All right, now let's look at this next one. 4. Example 4 here, the area is not actually to the left, it's to the right. So there's a couple ways we can tackle this, and I'll show both of them to you. What I could do is I could figure out how much area is to the left of z equals negative 1.75, and I could subtract that from 1, and that'll tell me the area that's to the right. And I'll show that to you this way. We could say 1 minus the normal CDF. The lower bound will still be negative 1e to the 99th power. The upper bound will be that z-score, negative 1.75. The mean and the standard deviation will be the same, okay? And so if I type this into my calculator, I get 1 minus, let's go ahead and do this. I'm just going to reuse, I'm going to go to second entry. I'm going to change that z-score to a negative 1.75, put a comma, 0, comma, the standard deviation, which is 1, and close that with a parenthesis. And we're going to get 0.0401. Wait, is that right? Yeah, because this 5 would bump this 0 up to a 1. Okay. So if I did this subtraction, I think this is going to give me 0.9599, I believe. But let me just go ahead and check. Yeah, okay. So this is the area to the right. Okay. This is close to negative 2, so 2 standard deviations below the mean, that's pretty far. And so all the area to the right of it is going to be a lot. Okay, it's almost 96%. Now the other way to do this would be, you could use your normal CDF function again, but you could let your lower bound be this z-score, and then you could let your upper bound be positive infinity. So instead of putting a negative 1 e to the 99, you could put a positive 1 e to the 99. Okay, this would be like positive infinity, and this one up here would be like negative infinity. And then of course these other parameters would just stay the same. And this will give it to you directly. That's a nice thing about these newer calculators. Used to, you had to find the area to the left and subtract that from 1 to get the area to the right, but you don't have to do that anymore. So I'm just going to completely redo this one, because my lower bound, I want to delete that negative. I'll just delete it. Okay, so now, or no, the lower bound is negative 1.75. Yeah. And our upper bound is now positive 1 e to the 99th power. Okay, and then these parameters are going to be the same. So hit enter, and look, we get the same thing, 0.9599. Okay, or in other words, about 95.99%. Alright, and then example 5 here. Example 5 here, guys, we're not going from negative infinity up to a specific z-value, nor are we going from a z-value up to positive infinity. We're actually trying to find the area between two specific z-scores. 0, which is the mean, up to 2.16. So we can do this directly. So my lower bound now is just 0, and my upper bound is 2.16. And again, keep these parameters the same, paste that in there, and we get about, this is close to 50%, and the reason is because 2.16 standard deviations above the mean, that's the majority of the right side of that tail, okay? So that's why this is close to 50%, but I can do this one the same way I did that last one. Normal CDF, the lower bound is 0, the upper bound is 2.16, the mean is 0, and the standard deviation is 1. Okay, and we ended up getting 0.4846. Okay, or in other words, 48.46% roughly. Also, you'll want to pay attention to your rounding when you start working on your homework. All right. Well, we've got a number 6 here. Let's go ahead and do it. It's just like this last one. Okay, and then we'll look at these last few. So this one's not taking me as long as I thought that it would. Okay, so for this last one, again, we'll use the normal CDF. Our lower bound is now a negative z-score. Our upper bound is 0. The mean and the standard deviation are exactly the same. Okay, so I'm going to use my calculator. -2, whoops, 2.29. Upper bound is 0 now, and then of course my distribution parameters are exactly the same. So type this in, and here again we get close to 50%, don't we? Actually, we're a little closer to 50% this time. So what would I round this to? If I went to 4 decimal places, the 8 would bump the 9 up to a 10, which would bump the 8 to a 9. So this 89 would become 90. So 0.4890. Okay, or in other words, 48.90%. Now, you may be wondering, why am I keeping the 0 at the end there? That shows that this is accurate to within 2 decimal places right here. That's why you keep that 0 on. If you throw the 0 away, you assume the rounding occurred right here, and it's only accurate to 3 decimal places right here as a decimal. Okay. But anyway, that's some practice using the standard normal distribution to find areas under the standard normal curve. Okay. So now what we want to do, let's see, what could we do? This is just some more on the calculator. We've already gone over this. I think what we will do here is let's go ahead and do 8, 9, and 10, and then we'll do number 7. Okay. So number 8. It says find the indicated probability using the standard normal distribution. Well, this means the indicated probability that z is greater than -2.72. What this equates to, guys, is finding the area to the right of -2.72. Okay. So in other words, if -2.72 is here, the area to the right is almost the entire distribution. So I'm guessing we're going to get a value that's relatively close to 1. Okay. Now we can do this in our calculators as well. We can do the normal CDF. The lower bound, though, is the -2.72. The upper bound will be the 1e to the positive 99, and then you're going to keep these parameters the same. Okay. And you just put this into your calculator. Okay, -2.72. And then the upper bound is 1, 99, yeah, look at this. We get a number. It's really close to 1, isn't it? Okay, so this is the way you would write it, though. You say the probability that z is greater than negative 2.72 is equal to 0.99. Let's go to 4 decimal places, 6.7 rather. Okay. All right, and then very similarly for problem 9, I'll draw you another little curve here for this one. So for this one, 0 is right in the middle, and then negative 0.18 is just to the left of it. Okay, so really we're trying to find how much area is in this little slice right here. So you're going to do this one the same way. You're going to use your normal CDF function. Your lower bound will be negative 0.18. Your upper bound will be 0. And then those parameters will be the same. And when we solve this, we'll be finding the probability that 0 is within that interval, somewhere between negative 0.18 and 0. Okay. I don't know why I drew a curly brace right there. It should be a parenthesis. Okay, so my lower bound is negative 0.18, and then my upper bound is 0, and then again my parameters are the same. Type this in. Yeah, you shouldn't expect much area here, right? Because negative 0.18, that's real close to the mean, so we're not talking about a huge swath of this curve. So 0.07, there, 0.07, we'll go 1.4, okay, so about 7%. And then finally, this last one, the probability that z is less than negative 0.62 or greater than positive 0.62. Okay, so I'm going to draw us another standard normal curve. So let's say that negative 0.62 is right here, and we're talking about the area to the left. And then positive 0.62 is over here. And because we want to find the probability that z is greater than, we're trying to find the area in this right part of the curve. Okay. Now I want you to notice that the amount of area that's in the left tail will be the same as the amount of area that's in the right tail. So what you could do is just find the amount of area that's in one of these tails and double it. Or you could think about that addition rule. The probability that z, because these are mutually exclusive events, z cannot both be less than this value and greater than this value. So the probability that z is less than negative 0.62 or greater than the positive 0.62 is the same as the probability that z is less than negative 0.62 plus the probability that z is greater than the positive 0.62 using the addition rule, if you guys remember that from section 3.3, because these are mutually exclusive events. But again, what you could do is just find the probability or the area in one of these tails and double it. Okay. I'll do the normal CEF. So the left tail, we would be going from negative infinity, that would be our lower bound, up to negative 0.62. Okay. I paste that in there, I get 0.2676. Okay. Plus, now I know this next one's going to be the same because this standard normal curve is perfectly symmetric. But just to prove it to you, I'm going to go ahead and do it anyway. So in this other case, my lower bound would be the positive 0.62, and my upper bound would be the positive infinity. Okay. And then, of course, my distribution parameters would be the same. And yeah, it's the same number, isn't it? 0.2676. So if you notice this when you're doing your homework, guys, that these are symmetric and that the area under each of these pieces is the same, then just find one and double it. So if I double, well, yeah, I'll go ahead and say times 2. Then we would get 0.5353 roughly. Okay. All right, so that's some more practice finding the. So remember, with this example, we've actually related the area under the curve to the actual probability that z is within that certain interval. Okay, and what that means is from the actual raw distribution of values, that means that x would be within a certain value. Okay. We'll talk more about this later on, but anyway, let's look at this example 7, and then I think we'll call it quits. All right, so it says a standardized exams scores are normally distributed, and this is very common. Okay, in a recent year, the mean test score was 1497, and the standard deviation was 320. The test scores of 4 students selected at random were, etc. Find the z-scores that correspond to each of these values and determine whether any of the values are unusual. So see, these numbers are from the raw data, from the actual distribution itself. When we turn these numbers into z-scores, then we're talking about the standard normal distribution. Okay. All right, now to turn these into z-scores, you have to remember this formula. Z is equal to the mean, or writing that backwards, the actual value minus the mean divided by the standard deviation. Okay. So for the 1910, that's the actual raw score minus the mean, which is 1497, and then divided by the standard deviation, which is 320, and excuse me, the z-score that corresponds to 1910 is going to be, we'll do this in the calculator, 1910 minus the mean, 1492, and divide that by 320. This is the z-score. So that means this student scored 1.3 standard deviations above the mean. Okay. So I'll say 1.306 equals z. Okay. And then we'll do the same thing for the next one. A score of 1260 minus the same mean divided by the same standard deviation. Now, since this raw score is actually less than the mean, we should be expecting a negative z-score. And well, since I didn't type all of that in, let me type it all in correctly in one step. Then I can reuse this for my next one. 1492, close those parentheses, divide by 320, and they get a negative 0.725, which is what we were expecting. Negative 0.725, okay? You can even say z of 1260, and this would be a z of 1910. So you can think about this as kind of like a function. It takes the actual raw score and it converts it into a z-score, so it's like a z function. And then for the last two, this student did really well. Okay, so now I can use my calculator. I can hit second entry, and I can just go back and replace that one raw score instead of having to retype everything. So 2190, and then I can hit enter. And yeah, this one would be, well, we'll say 2.18. Okay, is equal to z of that particular raw score. And then finally, the last one is 1400. So this one too is actually below the mean. So this should be a negative z-score. And then I can do the same thing with my calculator. Second entry, go back and replace that actual test score with raw test score with 1400. And guys, if you remember taking those standardized tests when you were a kid, it would, the results, it would give you a raw score, and then it would give you a percentile. Okay, well, the raw scores, like these raw scores right here, when you convert them into z-scores, then you can find the percentage or the percentile associated with that z-score, or in other words, how much area is to the left of a z value of 2.18, and that's how you can really kind of compare yourself with the rest of the test takers. And so we get a negative one here, negative 0.28 okay, is equal to z score of, yeah. Okay, so which of the last part of this question says, determine whether any of the values are unusual. Well, if you think back, we said that any score or any data value in a distribution that is 2 or more standard deviations beyond the mean, those are deemed unusual. Okay, and so there's only one of those scores, and it's this one right here. It's this one right here, because see, the z-score is 2.18. It's pen here is not working. I'm still not wanting to work. Well, my mouse is still working, so I will say, I'll just circle this score right here, and I will say that it is the one that's unusual. Okay. Unusual doesn't have to be a bad thing, right? It just means it's not usual. And in this case, I would think it's a very good thing. This person scored well above. This person probably scored like in the, if you think about how much area would be to the left of 2.18, it's more than, it's probably like 98%. So this person scored around a 98th percentile, which is fantastic. But anyway, guys, a lot of this section is just calculating the area under the curve, okay? Which which corresponds to the probability that z lies within that area. Now, in the context of this problem right here, you could say, what's the probability that somebody scores above a 2190? Well, that would be the equivalent of trying to figure out how much area is to the right of 2.18 underneath the standard normal curve. Okay, it's going to be a very, very little area. But anyway, I hope some of this is making sense conceptually. Okay, and remember, this normal distribution, guys, is common, very common in nature. We see it all the time. Typically things that are affected by many different variables tend to be normally distributed. So anyway, I'm going to go ahead and end this one, and I'll see you in section 5.2.